So I don't see the full screen anymore.
Hello, Norbert. Is everything okay?
Yeah, I don't see the full screen at the moment.
What? You mean the PPT file?
Yeah, I don't see the PowerPoint at the moment.
Oh, okay, no problem.
Yeah.
Okay.
Okay, yeah, perfect. Now I see this one perfectly. Excellent. Okay, let's see. Question is, are we already live in streaming for YouTube?
Yes, we're all ready to go. Please start.
Okay, excellent. Then, yeah, I would like to welcome you all to this session. This is actually the last invited talk, and then it's a talk that I'm very much looking forward to. So I'm happy actually to introduce to you Xian-Bin Wang from the Tsinghua University, who is one of the very early people working in the field of quantum key distribution, especially starting with the decoy state method, where he actually contributed essentially to that. And so I'm very much looking forward to his presentation. For the procedures, as usual, we have the Slack channel. If you have any question, just feel free just to go to the Slack channel and to post your question to your comment. And I will then basically at the end of the presentation actually go through these questions. You can as well, otherwise I think you can raise your hand in the participant list, and then as well we can actually give you the word to ask your question as well live. But for now, as I'm looking forward to your presentation, Xian-Bin, please go ahead.
Okay. Many thanks to Norbert for your kind introduction to me. Okay. Hello, everyone. Good afternoon, good morning, and good evening. I am Xian-Bin Wang from Tsinghua University. Thank the organizer for inviting me here to present my talk on practical long-distance thin field quantum key distribution through sending or not sending. Here is the outline of my talk. I will first shortly review the major methods and the results of quantum key distribution prior to TF-QKD. There are the decoy state method and MDI-QKD. After that, I will introduce, after that, I will go into the major content of this talk, the thin field quantum key distribution through sending or not sending. I will report both the theoretical results and experimental results with sending or not sending, including those long distance experiments with key rates exceeding the plot bound and those field test experiments. Finally, I reported the side channel-free quantum key distribution, an important variant of the sending or not sending protocol. Let me start with the BB84 protocol. In the year of 1984, these two gentlemen proposed the historical idea of doing secure private communication through transferring photons, which is well known as the BB84 protocol. Up to now, much progress have been made for the practical quantum key distribution. In particular, there are two major steps here: the decoy state method for quantum key distribution with imperfect single photon source, and the MDI-QKD, which is secure under whatever attack to the measurement device, even though it is controlled by Eve. Here are some major methods in practical QKD: the decoy state method, the measurement device independent QKD, and then very recently the twin field quantum key distribution. Let me start with the decoy state method. In practice, we don't have perfect single photon source. If we simply go ahead to take the BB84 protocol with the imperfect source, such as the coherent states, the security is threatened by the photon number splitting attack. By this photon number splitting attack proposed by a number of persons, including Norbert Luckenhaus, the chair of this session. Under this attack, the key rate and the security is losing a lot, and the key rate is actually in the scale of eta square. That's the square of the channel transmittance. Surely, this severely limits the practical application of QKD. Luckily, with the decoy state method, one can go ahead to use the imperfect single photon source in practical QKD with a key rate in linear scale of eta, the channel linear to the channel transmittance. The implementation of the decoy state method is very simple, just switching the intensities of source light among a few values. The net result is equivalent to the case that we have only used those single photon pulses in our source in the quantum key distribution. The decoy state method has been extensively applied in long distance QKD in practice. The decoy state method is successfully applied in satellite-based QKD with a final key rate around 1,000 bits per second. Then at that time, that is at the time of 2017. The most recent result is larger than this by 1 magnitude order. In the satellite to ground QKD application, the intensity fluctuation has been considered, which improves the practical security level. The result is secure even though there are small errors in the intensity control in decoy state method. Okay, for details, one may refer to these two articles. This is a picture of the satellite to ground quantum key distribution. Very recently, an experiment was done on the integrated system of space to ground communication. The communication network over 4,600 kilometers. This is published, the result is published in the paper this year. Of course, there are many other applications of the decoy state protocol. The decoy state method has been extensively applied on Earth. in more than 100 quantum key distribution experiments. For example, the experiment over 420 kilometers distance by Xian-Bin group, okay, and the QKD networks, a number of QKD networks by in Europe, by USDC team, by Japan and Europe joint team, by Toshiba, Cambridge, and so on. Also, there are some, here are a list of some early experiments. Due to the time limit, I cannot read them one by one. Besides source imperfection, there are also security loopholes in the limited detection efficiency. This problem has been thoroughly solved by the MDI-QKD, the measurement device independent quantum key distribution. MDI-QKD is secure under whatever attack to measure the device, including the case that EU fully controls the detectors. It is secure under all types of attacks to detectors, such as the one by Nielsen and Courses. Combining the decoy set method, secure MDI-QKD can be met with imperfect single photon source. A moment later, I will introduce the very efficient protocol. We name it as the 4-intensity protocol with 4 optimization proposed by our group some years ago. In the MDI-QKD, the key rate is also in the linear scale of channel transmittance. So to make it useful in practice, we have to first apply the decoy set method to its source so that it can be applied with imperfect single photon source. We presented the first analytical formula for the decoy set analysis with only a few decoy states for the MDI-QKD. We use a 3-intensity protocol for the decoy set analysis. This the formula and the 3-state protocol has been applied successfully by Calgary Group in Canada in the early demonstration of MDI-QKD. However, there are still some major problems for MDI-QKD in practical application. These major problems are the low key rate and the finite key effects. However, the finite key effects can be taken by the entropy analysis by the following literature. And also specifically for MDI-QKD, theoretical result for finite key effects has also been presented by Curti and Courses. But due to the high error rate in the X basis, say the error rate can be, the observed error rate can be as high as 25%. The key rate is still pretty low. So this is a last barrier for practical application of MDI-QKD. Then here we present the solution to this major problem for the low key rate, and we can improve the key rate greatly by magnitude orders. The major steps are here: the global optimization in parameter choosing. Then we consider the joint constraints in the finite key analysis. And finally, we use a 4-intensity protocol using biased basis with 4 optimization. Here is some result. This is the result of global optimization method by Toronto Group by Shifu and Courses. Here we compare. We use the joint constraints. We consider the data from different sources as one set and consider statistical fluctuation for the data in the set. Okay, then that is to say we consider data jointly. This adds many new constraints and makes the estimation tighter. This improves the key rates by about 2 times. This is our result of joint constraints, and this is the blue dashed line is is a result by Xu and co-authors. The joint constraints alone is not enough to improve the QCrypt. Okay, to make it practically useful, we still want to greatly improve the QCrypt. For that, we use the 4-intensity protocol with 4 optimization. We take a global search for parameter values. We take joint constraints from finite key effects. We take one parameter scan. We scan the one undetermined parameter for the worst case results directly pointing to the final QCrypt rather than the worst case in each step. So here is the QCrypt of our 4-intensity protocol. And this, the blue dashed line is our earlier results with joint constraints only. And the lowest, the dotted line is the results by Xu et al. So we see that by using the 4-intensity protocol with 4 optimization, the QCrypt has been drastically improved. Say in some typical distances, the QCrypt is improved by 1 to 2 magnitude order. So far, this 4-intensity protocol has implemented and applied by many experiments. For example, the high-speed experiment by Toshiba Cambridge, and the long distance QKD, a distance longer than 400 kilometers by USTC, the RFI MDI-QKD experiment by USTC, another group of USTC, and the MDI-QKD digital signature, the first free space MDI-QKD experiment, and the on-chip MDI-QKD experiment by Bristol, on-chip MDI-QKD experiment by USTC, also on-chip MDI-QKD experiment by NTU group in Singapore, and also the gigahertz MDI-QKD experiment by Toshiba. The MDI-QKD with malicious device, the experiment by jointly by USDC and European groups. Here, this is the experimental result of MDI-QKD by using our 4-intensity protocol over a distance of more than 400 kilometers, the longest distance at that time. And also in this work, they have also redone the experiment with redone the experiment over the distance of 200 kilometers. They find an improvement in the QCrypt by 500 times. Also, the experiment has demonstrated that by using our 4-intensity protocol, the QCrypt of MDI-QKD can break the distance limit of BBID4 even with perfect single photon source. So this demonstrates that the MDI-QKD is indeed practically feasible. Moreover, in this year, we further improved our method by the double scanning method. We take the scanning to 2 parameters. We still use the 4-intensity protocol, and we have improved the QCrypt by 100% and even more in some distance. Here is the TF-QKD. If we want, just now, although we have had some efficient protocols by Decoy state method or by the 4-intensity protocol of MDI-QKD, the QCrypt is still in the linear scale of the channel transmittance. In the year of 2018, something happened, something very important happened. That's the thin field quantum key distribution. The QCrypt is demonstrated to be improved from the linear scale of channel transmittance to square root scale of channel transmittance. And also the QCrypt can break the pro bond, which is the upper bound for repeaterless QKD. There are also after that, there are also a number of variants of TF-QKD. For example, the SNS, sending or not sending protocol, which I will introduce in detail, the CAL protocol, and the MPP, non-post selection, and the TF star, and the phase matching. There are, notably, we have important variants. For example, the sending or not sending protocol and the CAL protocol. These two protocols are secure against the general attacks and robust to channel noise and finite key effects. Let me very briefly introduce this sending, the main idea of sending or not sending. Actually, it is the encoding states are the single photon states. But we only use the single photon interference in X basis. In Z basis, there is because there is only one side sends the state, so there is no interference in Z basis. This makes the fault tolerance property of our sending or not sending protocol. And also in our protocol, we only use the single photon constituted in the coherent states. The traditional GLLP model directly applies for the decoy state analysis. This can bring a lot of advantageous results for the analysis. For example, the finite key effects analysis. The secure key rate and distance is greatly increased compared with the MDI-QKD protocol. The key rate in particular, by our numerical simulation, we show that the key rate at 400 kilometers is increased by 5 to 6 orders of magnitude. And then 1 year later, we further developed the method by taking the error rejection with two-way classical communication. We can improve the sending probability and hence further raise the final key rate and also the distance. There are 3 methods for the error rejection. First is the SNS protocol with standard error rejection. This can improve the key rate at the longer distance rhyme and improve the distance by 50 kilometers. The SNS with odd parity error rejection. This is some new type of error rejection proposed by ourselves. It improves the key rate in the whole distance rhyme by about 40% and improve the distance by 50 kilometers. And finally, the actively odd parity pairing. So we actively make the odd parity pairing. This will improve the key rate in the whole distance rhyme by about 80% and improve the distance by 50 kilometers. The paper is finally published last year. Okay, these are comparisons with different methods, and we find the LOPP method, that is the actively odd parity pairing, is the best. It is this dashed line. Of course, we find that all our methods can break the pro bond, both the absolute pro bond and the relative pro bond. Then the next question is how to take the finite key effects. For SNS protocol with original post-data processing, the finite key effects are studied in the year of 2019. For SNS protocol with error rejection in post-data processing, the finite key effects are studied very recently, one in last year and the other this year. Here, there are something non-trivial is that the data from the pairing are correlated. So the statistical fluctuation is not so easy. We constructed some mathematical theorem by ourselves and then apply those mathematical theorems to study the statistical fluctuation here. Also, there are some other results that is not for SNS. such as the MSK results by this gentleman. And also for CAL protocol, the finite key effects has been also studied this year. Okay, these are some comparisons of the key rate over different distances for different protocols. In this comparison, we have already taken the finite key effects into consideration. We find that the LPP protocol, this red solid line, is the best. Okay, and this black solid line is the original SNS protocol, and this is reference 22. That is the MSK protocol, MSK result. There are a lot of experiments for the SNS protocol. The SNS protocol for TF-QKD has been implemented successfully in many experiments, including 4 of them exceeding 500 kilometers in the distance. 1 of them exceeding 600 kilometers. And also, very importantly, 2 field tests through commercial optical fiber between metropolitans Jilan and Qingdao, the 2 big cities in Shandong province, China. These 2 field tests by SNS protocol are the only field tests of TF-QKD so far. This is the picture for the setup of the experiment over 509 kilometers distance by using the sending or not sending protocol, the SNS protocol. The result has been published last year. In that work, the USDC group, they have besides the 509 kilometer distance, they have also done the experiments over other distance. For example, the 408 kilometers. In this experiment, at this distance, we obtain a Q rate of 4 magnitude order higher than our 4 intensity MDI-QKD experiment taken in the year of 2016. Here are 2 experiments done by Toshiba Group this year. They also use the TF-QKD through sending or not sending. They have completed 2 experiments. One is the 600 kilometer distance. The other is 550 kilometer distance. At this 550 kilometer distance, they have fully taken the finite key effects. The results has been published in Nature Photonics this year. And also here is a picture of the field test of TF-QKD through sending or not sending protocol over a distance of 511 kilometers between the 2 big cities, Jilan and Qingdao in Shandong province. The results has been also published in Nature Photonics this year. And moreover, there is another field test of TF-QKD using sending or not sending protocol. That is 428 kilometers, also between Jilan and Qingdao. The result has been the experiment. They use different experimental realizations. Okay, the experiment result has been also published this year in Physical Regulators. Here is a summary. Here is a summary of the major experiments in TF-QKD in thin field quantum key distribution. In this table, we have listed the long distance experiments. From this table, we can see that so far there are 5 on-Earth QKD experiments exceeding the distance of 500 kilometers. 4 of them are done by our sending or not sending protocol. And also there are the 4 longest distance experiments. There are these 4, the 600 kilometer experiment by Toshiba group, the 550 kilometer experiment also by Toshiba group, the 511 kilometer experiment by USDC, 509 kilometer experiment also by USDC. In these 4 experiments, 3 of them have strictly taken the finite key effects. All of them have exceeded the Pro bound. Here is another table for other experiments of thin field quantum key distribution. Some of them are proof of principle experiments. Some of them are over a distance of 300 kilometers and 400 kilometers. Some of them are done by sending or not sending. Some of them are done by CIL protocol proposed by Curti, Ajuma, and Lowe. And also one of them is done by the MPP, non-post-selection protocol. Here is a list of field test result of the TF-QKD experiments. As I have said, there are 2 experiments here, field test. Both experiments are implemented by our sending or not sending protocol. So far, they are the only field test experiments for TF-QKD. The field test results here is very important. These results conclude that TF-QKD is feasible for practical application. Finally, I want to talk something about the side channel free quantum key distribution as an important application of the idea of sending or not sending. So if we use the sending or not sending protocol without a decoy state method, we can actually realize the very important result of side channel free quantum key distribution. First, let me show what is side channel. The subspace except the encoding space, that's the side channel space, such as the frequency spectrum, the emission time, the spatial angular momentum, and so on for the pulses. The security in the operational space does not guarantee the security in the whole space, including the side channel space. So, and also we say that the side channel is inevitable given realistic sources. The key idea of our side channel free protocol is this. We assume there is an ideal source. We say it P. Of course, this is a virtual source. This ideal source corresponding to the realistic source S. In practice, we only have this realistic source S. If the pulses of S, the realistic source, can be mapped into that of P with a quantum process M, then the security of the protocol using these 2 sources is equivalent. Okay, this we use this idea. In our side channel free QKD, we use the idea of sending or not sending. In the protocol, Alice and Bob only decide sending or not sending a coherent state. There exists a unitary transformation to map ideal source states to states in the to the real states in the whole space, provided that the 2 source states have the same probability distribution in photon number space. This in our protocol, the photon number space is the operational space. Okay, we find there exists a unitary transformation for this. Since the security of real states is equivalent to the security of perfect states, we now only need to consider the source states in operational space. In our real protocol, we use these 4 states. This 0 alpha B means at a certain time window, Alice decides not sending, Bob decides sending a coherent state. And also both of them decide sending a coherent state. And this means both of the, this means both of them decide not sending. For this means both of them decide sending a coherent state. this real source states, it's easy to show that these real source states include a virtual subsource state, or in this form, the three different states in this form. And the security with these states, the virtual states, the subsource, can be proven strictly. And also the phase error rate in the real protocol can be estimated by the worst case study. So here is our conclusion. The protocol is secure if we can prepare exact vacuum in the operational space for those time windows of not sending. And also another condition is that if cannot attack inside Alice and Bob's lab, we can compare the security of different protocols. This, in particular, we compare the security level of our side-channel-free QKD with the DI-QKD. If we only compare our side-channel-free QKD with MDI-QKD or TF-QKD, the advantage is obvious because our protocol is both measurement device independent and source side-channel-free. Comparing it with the device independent QKD, we find that our protocol has an advantage in measurement device independent. But for DI-QKD, it is not measurement device independent. However, comparing with DI-QKD, our protocol has a drawback, that is, although it is side-channel free, however, it is not source device independent, but DI-QKD is source device independent. Okay, and also we have a very important advantage is in the achievable distance. In our side-channel free QKD, we only suppose the existing technologies such as vacuum and non-vacuum coherent states, and the distance. By numerical simulation, we show that the distance can be larger than 200 kilometers. However, the DI-QKD by existing technology, the distance is shorter than 10 kilometers. Okay, here is a very recent experiment. The side-channel free quantum key distribution experiments done by the USDC group. They have just completed 3 distances for the side-channel free quantum key distribution, of which the longest one is over 50 kilometers, the distance, the secure distance. Okay, that's my talk. Thank you very much.
Okay, great. Thank you very much, Xian-Bin. I just wonder whether the audience has any questions at this point. So, as I said, basically, please use the Slack channel to post your comments or questions, or raise your hand in Zoom. And maybe for me to pick it up with the first question of that came to my mind, and that is you talk about this side-channel free version. It was not clear to me. Is that essentially the sending protocol, or is it really, do you have to modify the protocol to get this kind of properties?
It's essentially the idea is just sending or not sending. However, there are a little bit of modification. First, we don't use decoy state method, because if we use a decoy state, we cannot control the side channel space. And also the poster selection, the method for poster selection is a little bit different. Okay, that is because we want to make the side channel free. So the poster selection is a little bit tighter than the original sending or not sending.
Okay, great, thank you very much. Then there's a question from Vadim Markov. Vadim, if you can unmute yourself and ask a question.
Yeah, thanks. So with this latest protocol, which hacking attacks remain possible?
As I have said, this is side channel free. However, it is not source device independent. When we say side channel free, we mean that we disregard the side channel of the source state itself. However, if you attack inside Alice or Bob's lab, if Eve can actively change something in the source state, then the protocol is still not secure. We have a condition that Eve cannot attack inside Alice and Bob's lab. But he can make use of the side channel space of the source state. Okay.
So essentially, the only type of attack remaining for the hacker is an active attack on the source. So different kinds of Trojan horse or injection attacks. Is that right?
We cannot resist the photon injection attack. We cannot. Yes, you're right.
Okay, great. Thank you very much. Then Marcus Curti, you raised your hand.
Hello. Well, first of all, I would like to congratulate Xian-Bin Wang for the nice presentation and the great results.
Thanks.
Actually, my question was similar to that of Vadim, because from your statement you put some assumption, and I wanted to clarify what it means, these assumptions. As you mentioned, for instance, Trojan horse attack are not included in what you call side channel free QKD. I was wondering, for instance, whether correlations between pulses are included. Because it seems to me that your analysis basically kind of include state preparation flaws, in the sense that what we could call mode dependency, the fact that the source might encode information in various degrees of freedom, and for that your protocol is very robust, but not for any kind of side channel. And I think it would be nice to clarify that. And there are also protocols that have been recently suggested that kind of cover further sides of side channel, including, for instance, Trojan horse attacks, mode dependencies, and so forth, that have not been mentioned.
Oh. Well, we proposed our side channel free protocol rather early. That's in the year of 2018, and we published last year. I noted that there is an article published in Paper Review Applied this year. Okay, we are studying that. There are also that is also talking about the side channel effects. Yes, indeed. I know that there is a new article published this year. Here, when I say side channel free, I mean that in a normal protocol, even you can prove its security in operational space. However, if can take information in the side channel space, for example, in the BB84 protocol, even though you prove its security in the polarization space, however, if can distinguish two photons by the imperfection in the frequency in their frequency spectrum, things like this. I don't include that the case such as photon injection. That means if can attack inside Alice and Bob's lab. Here when I say side channel free, okay, I mean for the source states, if you only need to prepare them exactly in the operational space, you don't care about any imperfection in side channel space. That's all.
Thank you. That is what I meant. For instance, because there might be other side channels, let's say in the power consumption, let's say that maybe it leaks some of the settings that you select, or these kind of side channels are also not included as far as I understand. So it's more a question of mode dependency, of encoding the information on the quantum state using different degrees of freedom. As you put the example, maybe you want to use polarization, however, your device is imperfect and also changes slightly the frequency depending on the polarization state. Thank you for the declaration. And thanks again for the nice talk.
Okay, thank you. Thank you for the question.
Okay, then thank you very much. So then the next question comes from Hoi Kwong. Hoi Kwong, please.
So first off, thank you for your nice talk. It's very congratulate you on a very nice result and very nice talk. It's very impressive. I'm trying to follow up on Marco's question about a side channel, right? For the first QKD experiment, right, there's a side channel SAN, right? So when a device, right, for example, send a signal, right, maybe make some noise, right? So I'm sending or something, right? Or it's not, I'm not sending. So that could be a side channel, right, in the QKD system, right? So I'm just confused. So does your protocol protect against this kind of side channel or not?
I'm not quite. First, thanks a lot to Hao Guang for the question. I'm not quite clear of the question. When I do you mean the definition of side channel free, or?
I mean, what if the side channel is some additional degree of freedom, right? So maybe some noise or some X-ray.
Oh,
right?
yeah. I only mean that. I mean that. Yeah, additional. We don't care about any additional degree imperfection of our states. I mean, I simply mean this.
Okay, but if there's no imperfection, of course, there's no side channel, right? So I'm just confused what you mean by side channel free.
We define we define the side channel free. I mean, we don't worry about we don't have to worry about any imperfection in the additional space, in the additional dimensions. That's what I mean.
Okay. Great. Thank you very much. Are there any additional questions? I don't see anything on Slack at the moment from the audience. Any last question? So that seems to be not the case. So I really would like to thank Xian-Bin again for his presentation, for really this large number of really great results that you presented over here. And I would like to remind everyone basically that we have the chance now in the next break as well to go into the speaker lounge. If you go through the web page of the conference, there's a speaker lounge on the same page as the main meeting. And so that is the opportunity as well to ask further questions to Xian-Bin and have more discussion.
Okay.
So thank you very much. And see all of you then after the break in the next session of the contributor talks. Thank you. Bye-bye.
Okay. Thank you.